Hello, my name is Rakesh Ravi, and in this video we'll be talking about the Lab 2 charged tapes revisited. In this lab, I modeled two charged plastic tapes as uniformly charged lines and used a computational model to estimate the total charge per tape needed for the top tape to float. In the balanced run, the electric force on the top tape is about 1.99 times 10 to the negative 3 newtons, and the weight is around 1.96 times 10 to the negative 3 newtons. These values are essentially equal, indicating vertical force balances with the downward force. The goal of this lab was to model two tapes that exert electric forces on each other and estimate the charge necessary for the top tape to float above the bottom one. Float here means that the upward electric force matches the downward weight. And this analysis used Coulomb's law, gravity, and superposition with an emphasis on equilibrium. I compared a point charge model to a line charge model because the line charge model ended up being a better representation of a real tape at this distance. I first prepared the tapes by pulling them apart to charge them. One tape was fixed and the other one was allowed to float. I recorded the separation where floating occurred and then used a computational model to infer the required charge per tape at that separation. In the model, I used tape length equals 0.2 meters, width was 0.019 meters, mass was 2 times 10 to the negative 4 kilograms, floating distance was 0.03 meters, and the gravitational acceleration was 9.81 meters per second squared. For calculations, we used the force of gravity equals mg and used that to calculate 1.96 times 10 to the negative 3 newtons. And then for the charge, we used F equals QE equals kq squared over r times square root of r squared plus L over 2 squared. And then we use that to isolate q and solve for q, as we knew the other values already. Alright, and here's from lab 1 where we estimated the point charge, which ended up being around 1.4 times 10 to the negative 8 coulombs. Alright, and in lab 2, we split that into many equal elements and summed the vector electric field from every bottom element to each top element. The code includes an electric field function, a line of charge constructor, and an arrow visualization to display fields and forces, which captures the finite length effects that a midpoint estimate misses. And here are the results. We can see that the electric force and gravitational force are around the same, and we can see that they both balance out correctly, which is reasonable. And here are some of our assumptions. One of them was both tapes carry equal charge, which may not be the case in a real scenario. The tapes' charge is uniformly distributed, and we ignored air resistance. For errors, we could have lost charge from tape handling, which would have made them not equal to each other, random and systematic errors such as measurement errors, and uneven charge distributions. Okay, and so what if we had modeled each of our tapes as a single point charge? All the charge would be concentrated at the center of the tape, which would be a charge of 1.4 times 10 to the negative 8. So the line charge model is around 2 times larger than that point charge model is, with a charge of 2.37 times 10 to the negative 8 coulombs. So why do these estimates differ? The point charge model compresses the charge into one location at the center, so it likely misinterprets the interaction distance and net force. Since the line charge model accounts for charge being spread along the tape, adding contributions from many different locations, its charge is more likely to be closer to the true value. That's it. Thank you for watching.